Welcome to this next video in the playlist on ring theory. In this video, what we're going to introduce is the concept of a polynomial ring. Now, a polynomial ring is a way of constructing a new, bigger, better ring from an initial ring. Okay, so to construct a polynomial ring, you have to start off with another ring. Okay, so I'm firstly going to start off with the setup, and I'm just going to recap the definition of a ring, and then we'll see how to go from this initial ring to a polynomial ring. Okay, now we're going to be working with a commutative ring rather than a general ring, so our starting point will be a commutative ring. Okay, so let me just recap the definition then of a commutative ring. So we'll call it capital R, and it's going to be some generic commutative ring here. Okay, so what is this fundamentally? Well, this is an algebraic structure, so it starts off its life as a set of symbols. That's the starting point for building any sort of number system. Okay, so you start off by building a set of symbols here, and you can make up these symbols, and I'll denote this set by this box here. So there's lots of symbols inside this set, and then we're going to define some interesting algebraic structures on this set of symbols to turn it into an actual ring. Okay, specifically a commutative ring. Okay, so what do we have to define then on this set of symbols to produce a ring? Well, we need to define two composition laws. Okay, the first is going to be called addition. Okay, and it will take the form of a great big composition table like so. Okay, so we'll call this addition, and I'll colour addition here in an orange. And this is going to be a composition where you can compose any element of the ring with any other element of the ring. Okay, so you need to have every possible addition defined. Okay, and that's what this addition composition table is going to do. What you're going to do is give every element of the ring a row dedicated to it in this addition composition table. So here are the rows, and every element of the ring will get a row dedicated to it. So you'll put every element of the ring in one row. Okay, then what you'll also do is give every element of the ring a column. So let me just draw on a few columns in my table here. So here are just a few example columns. Okay, and what you're going to do is give every element of the ring over here a column that will be dedicated to it as well. And then what you can do then is this table will now have an entry corresponding to every possible combination of elements from the ring that you can add. Okay, so if you want to know what some element little x from the ring added to some element little y from the ring is, what you do is you go to the row dedicated to the first element here, little x. So let's say that this is the row dedicated to little x. You then go to the column for the second element, so you'll go to the column dedicated to little y, let's say it's this one here, and then what you'll look for is the intersection of the row dedicated to little x with the column dedicated to little y. That's going to be this entry here that I've just highlighted in orange, and that will contain some answer, and that answer will be what x plus y is going to be defined to be equal to, and that answer will be back within the set capital R. So all the answers that you put in all these boxes in the addition composition table will be from the ring capital R. Thereby, because we've got a box corresponding to every possible combination that you can take of an element of the ring added to another element of the ring, you will have every possible addition defined in this addition composition table. Okay, now that addition composition table has to obey some incredible properties. Okay, and those incredible properties are the properties of an abelian group. So this addition composition table is the composition table of an abelian group. Okay, and if you're not familiar with the axioms that an abelian group must obey, please do watch my video on the definition of a ring. We go through all of the axioms in detail in that video. Okay, this is just supposed to be a recap. Okay, so it obeys the properties of an abelian group. Now, of course, if we just had that single addition composition law, then we just have a set of symbols with an abelian group composition law on it, and that would just be an abelian group. It would be no more than an abelian group. If we want to turn this into a ring, we have to have another composition law defined on top of the addition composition law. Okay, so we'll have our second composition law here. And this second composition law is going to be called multiplication. Okay, and I'll colour in multiplication here in pink. Okay, and again, multiplication is a composition where you can compose any element of the ring with any other element of the ring. So we need to define what any element of the ring multiplied by any other element of the ring is going to be equal to. And again, that will take the form of a great big composition table. So just as we did with addition, what you will do is you will dedicate a row to every single element of the ring. Okay, and like so, and you'll dedicate a column in this multiplication composition table to every single element in the ring, like so. Okay, and then once again, if you want to know what any element of the ring multiplied by any other element of the ring is, so if you want to know what x multiplied by y is, usually just written x and then having y next to it rather than actually putting the times symbol in there. Okay, that's just conventional. What you'll do is you'll go to your multiplication composition table here. Again, you'll look at the row dedicated to the element little x, the first element in this multiplication. You'll look at the column, dedicated to little y here, like so. You'll look at the intersection between the two, and that entry in this multiplication composition table, it will be back within the ring here, and that will be the answer as to what x multiplied by y is. So by having all the answers in every single one of the entries of this multiplication table, you define what any two elements of the ring multiplied together is actually going to give you. Okay, and that multiplication table must obey a bunch of axioms as well. So it must obey closure, which says that all the answers in the multiplication table must be elements of the ring, i.e. they can't be some symbol that's not in here. It must obey associativity, which says that if you multiply three things together, there's only one answer to that. It does not matter where you put the brackets. It must have a multiplicative identity, which we call 1, which is an element which will multiply either way round with any other element of the ring to give that other element of the ring back again. It must obey the two distributivities, which say that it doesn't matter whether you first add two elements together and then multiply, or if you firstly multiply and then add. And we're insisting that this is going to be a commutative ring, so we're going to insist that any element multiplied by another element, it doesn't matter which way round you do it. So x times y will equal y times x, but a more general ring doesn't need to obey commutativity. Okay, so again, if you're not totally familiar with those axioms, do watch the video on the definition of a ring. Okay, so there's just a little bit of a recap of what a commutative ring is, and we've now got a nice picture of our commutative ring here. So what we're now going to construct is the polynomial ring from this commutative ring R. So before I actually tell you what this is going to be, I'm going to give you the name for it first. So we're going to get over the name for it first, and then what we'll do is actually have a look at how we construct this thing. Okay, so the name, it's denoted like so. R, and then you put square brackets. So note these are square brackets, not curly brackets. Okay, so R square brackets x, and I would just read that as Rx rather than actually stressing the square brackets. Okay, but you could say R square brackets x. Okay, now the full name for this, the full name in words for this, is quite elaborate. It's the ring of polynomials in the indeterminate x over the ring R. Okay, so I'll write that out in full. Okay, so it's the ring of polynomials, or you could just say the polynomial ring. It doesn't really matter. The ring of polynomials, and then we've got in the indeterminate. Okay, so the indeterminate, I think that's how you spell that, indeterminate x over the ring R. Okay, so over the ring R. Okay, so that is the full name for this structure that we are about to create. Okay, but if you said the polynomial ring over the ring R, people would know what you meant. Okay, but that's the full name for it, the ring of polynomials in the indeterminate x over the ring R. Okay, so what actually is this going to be? Well, it's going to be a ring fundamentally. It is going to be a ring structure, and in fact it is going to be a commutative ring structure. Okay, so what we're going to do is we're going to take our original ring here that we've started off with, which was a commutative ring, and we're going to build a bigger, better one. Okay, this is going to be a bigger ring that's going to actually completely contain this ring here. So this original ring is going to be a sub-ring of our new ring here, and it's going to obey all of the axioms of ring theory. Okay, so if we want to build a ring, what do we fundamentally have to do? Well, we've just seen this. We have to create a set of symbols and define two composition laws on it, addition and multiplication, which obey the beautiful axioms that we want those laws to obey in order to be classified as a ring. Okay, so what we're going to start off with then is creating the set of symbols. So that's our first problem, and then we'll worry about how we're going to define addition and multiplication on. Okay, so what are the symbols going to be? Well, the symbols are going to be polynomials where the coefficients are in the ring R. Okay, now we are going to define polynomials from a very abstract point of view. Okay, so get rid of your preconceptions about polynomials. We are not doing calculus, okay? I do not care that all polynomials can be associated with functions. I'm just going to view polynomials as being symbols, okay? It's quite a refreshing point of view because you don't have to worry about them being anything more complicated. Just view them as being symbols. We are doing algebra, not analysis or not calculus or anything like that. Forget that we can represent or associate with all of these polynomials functions. Just view them as being symbols. Symbols on which we are going to define an addition law and a multiplication law. I'm just doing ring theory. I don't care about anything else at this point. Okay, so it's quite a refreshing point of view, but you do have to sort of abandon your preconceptions. Okay, so here comes then the formal definition of a polynomial. It is just a symbol, okay? A symbol, a complicated symbol that we are going to create from the symbols that are in our commutative ring, capital R. Okay, so what we're going to do then is we're going to use this new symbol x, okay? So we're going to use this symbol x and we're going to have powers of x, okay? And these are just symbols, okay? So we're going to have x0 rather, x1, x2, okay, so I'm just taking this symbol x and I'm superscripting a number in front of it, okay, a non-negative whole number, okay, so it'll be 0, 1, 2, and then you can go on, okay. Abandon your preconceptions. These are just symbols, they're just placeholders as far as algebra is concerned, okay, and it will go on and on and on. Okay, so now, what is a polynomial? Well, here is the formal definition of a polynomial. A polynomial, p of x, so we'll denote it p of x, is just going to be a symbol that looks like this. A sum from I is equal to 0 to infinity of things of this form, ai times xi. Okay, but again, you probably shouldn't view that as times. Just view it as I'm putting the ai next to the xi in this way. Okay, so this is what these are going to look like. And all of these ai's here, the ai's are all going to be from the ring capital R. Okay, and here's an important point. I only want a finite number of these to be non-zero. Most of these coefficients are going to be 0 from the ring, the additive identity from the ring. Okay, so finite number will be non-zero. Okay, only a finite number. Now, what does that mean? If only a finite number are non-zero, then I will get to some term where I have the highest power of x, which has a coefficient of non-zero, okay, and then all the other terms after that, all the higher powers of x, they'll just have the 0 coefficient, okay. So what that means is that more intuitively I can write this out as something of this form: a0 plus a1x plus all the way up to anx to the n, like so, where this is the last coefficient that is not 0, and then all the other coefficients after that will be equal to 0. Now note, it is not necessary that all of the coefficients in front of this one are non-zero. a0 could be 0, in which case I wouldn't bother to write it here. I'd only bother, if I was writing it out explicitly like this, to write out the terms which have a non-zero coefficient. So it's conventional not to bother to write the powers of x which have a coefficient which is 0 in the ring. Okay, you only write out the ones that are non-zero. Okay, and since there are only a finite number that are going to be non-zero, there will be some highest power of x, which is the last one that has a non-zero term, and therefore you won't have to write out any after that. Okay, so that's an important point. We're not doing analysis here. I'm not talking about polynomials which go on and on forever. Okay, I don't care about those. I just want it to have a finite number of non-zero terms. Okay, so just view these things that I am creating here as symbols. Okay, forget the plus and the times here. Forget your preconceptions of that. This is just going to be a symbol. These things are just going to be symbols. Okay, it's just a symbol on a piece of paper. Okay, so I'm creating things of this form, symbols of this form, where a finite number of the terms are non-zero, or a finite number of the coefficients are non-zero. Okay, so that's the formal definition then of a polynomial, that it's symbols of this form where you have powers of x with elements of the ring stuck in front of them, and then you put in between these terms of the polynomial plus signs, but don't get any preconceptions of that. It's just a symbol. Okay, and I realise that you will have lots of preconceptions. You'll be thinking plus times, but it is just a symbol. Okay, so this is the formal definition of a polynomial, that I am just creating symbols of this form. Okay, and I can create these symbols as long as I have my ring R. Okay, because everything else here doesn't rely on anything. Okay, I can use the symbol plus, I can use the symbol times. Okay, they are just symbols, and then I can just create things of this form. All that is then left is x and then the powers of x. So I suppose it does rely on you knowing the non-negative whole numbers. But apart from that, this is easily defined once you have your commutative ring structure. Okay, so that then is going to be the set of symbols that is going to underlie this new ring. And again, I urge you to, at this point, just think of it as a bunch of symbols. This is the formal abstract algebraic view of what a polynomial is. It is just a set of symbols. Okay, I don't care that you can associate these all with functions. I don't care that you can kind of view these as operations within the ring where x is just some unknown. Just think of it now as a set of symbols. Okay, right. Now some definitions before we go any further. Okay, so I want to give you the definitions of what the degree of a polynomial is, what the leading coefficient of a polynomial is, and what a monic polynomial is, before we then go on to discuss how I'm going to define addition and multiplication on this set of symbols. Okay, so firstly, the degree of a polynomial. Okay, so the degree of one of these symbols then in my new set that I'm creating. Oh, and I should just say, this set, the ring of polynomials in the indeterminate x over the ring R, it's going to contain all such polynomials. It'll be the set of all such polynomials. So p of x, which is of this form, I is equal to 0 to infinity, ai, xi. Okay, so this is just telling you how to create these symbols. It's just telling you the form that these symbols are going to exist in. Don't interpret it as any more than that. Okay, where, and can I squeeze this in? I'll do it just down here. All the ai's are elements of the ring, and we also have that condition that a finite number are non-zero. Okay, so you put all polynomials of that form into this set where the coefficients of the x powers, and I'll give you just the proper term, I don't know why I'm suppressing this from you, okay, these are called the monomials. These powers of x to a certain power, these are called the monomials. And I should also stress that usually you don't bother writing x to the 0, usually you just have the coefficient of x to the 0 on its own looking like a constant there, rather than actually putting in the x0. Formally, if you wanted to, you could put in the x0. That's another thing I didn't actually manage to get around to explaining at the time. Okay, so those are called the monomials. Okay, so it's all things of this form where you've got coefficients from the ring in front of your monomials, and then you're just putting them next to each other with this plus symbol in between them. But it is just a symbol, okay? Abandon preconceptions about what that means. It is just a symbol. Okay, so that then is going to be the set that I'm going to form a ring from. Okay, and now what I'm going to do is just give you a few more definitions with regards to polynomials. So we would say that all of the elements of this set are polynomials with coefficients in the ring R and in the indeterminate X. Okay, so the degree of a polynomial then. Okay, so this, hopefully you should have some understanding of this from classical algebra. The degree of a polynomial, the way I'm going to define this is just you go to the term in the polynomial which has the highest power of x, which has a non-zero coefficient from the ring. Okay, so you go to the last term in your polynomial which has a non-zero coefficient. What is the power of that term? What power of x is that monomial then? Okay, and that's what the degree is. So the degree here will equal n. Okay, so a very easy concept. Then another important concept, another important definition is the definition of what is meant by the leading coefficient of a polynomial. Okay, so the leading coefficient of a polynomial again refers to this final term, the term with the highest power monomial. Okay, so again you go to the final term with a non-zero coefficient from the ring, okay, and you look at what this coefficient is, and that is what's called the leading coefficient. So an is going to be the leading coefficient of this polynomial. It's the last coefficient in the polynomial in front of a monomial which is non-zero. Okay, and then one final definition which we will see in a lot in upcoming videos is the concept of a monic polynomial. And a monic polynomial is one where the leading coefficient, the last non-zero coefficient in the polynomial, is equal to the additive identity. So a monic polynomial, the leading coefficient an will equal 1. Okay, so that's the definition of a monic polynomial. And as I say, don't worry about obviously memorizing these definitions. We will be using them so much that you will just become familiar with them as we use them. Okay, but I'll state them all now because we will use those in later videos. We're not going to have much use for them here. This is just some introductory terminology. Okay, right. So we've now created this great big set of symbols which is going to contain all polynomials in the indeterminate x with coefficients from the ring capital R. What we'll do in the next video is we'll take this set of symbols and we'll define an addition law on it, and we'll have to make sure that that addition law is going to obey the axioms of an abelian group, and we'll define a multiplication law on it, and we're going to have to make sure that that multiplication law is going to satisfy the axioms that we need for a commutative ring.